recording again. So recording is on. And this time I will actually, just for fun, I will make a copy here. On the last exercise, I was doing the same thing as Juho did. And we were highlighting the text simultaneously on the same document. That looked a little bit funny. Anyhow, so exercise 8 is about serial interfaces. And as usual, read the instructions first. Okay, and that's actually, let me change this a bit. Exercise 8, not 4, the header. Okay, part 1 is serial data analysis. The following, there are 5 different oscilloscope traces of serial transmission. So that those traces are actually RS-232 without the voltage conversion. So low voltage is 0 and high voltage is 1. The data mode, 8 bits, no parity, 1 stop bit. So each byte, one start bit, 8 data bits, no extra parity bit, 1 stop bit. And the axis, vertical axis is voltage, 1 volt per square. 1 square, so this is 1, 2, 3.3 volts signal. And horizontal axis is 50 microseconds per square. And you need to basically analyze this oscilloscope trace. And that's actually something what you need also, independent of which major you are now focusing more to the smart system, or more to the this communication stuff. You will be familiar with these traces. So this is a good place to start reading them. So how to read this one? It didn't say anything about how fast the transmission is. So I would guess one of the questions here is what is the bit rate? Then another one is what is the message? So start bit, then 8 bits, and no parity bit, so that must be the stop bit. So that's start, that's stop, and now we are using the normal logic, meaning 0 is the signal at 0 volts and high is that signal at 3.3 volts. Okay, pretty straightforward. You just need to read the bits and translate that one into what is the message. Read what is the message on that one. Second, so we have, I think here we have, do we have second? Okay, 1, 2, 3, 4. Okay, it's just different value here. Or was it? Yes, and then we have another one. So decode these 3 cent variables or values. 4th byte. Okay, good. There are 5 bytes. That's nice. 5 consequent bytes. And what is the approximate baud rate? So speed of transition. How many bits per second? That comes from the how long is the one single bit. How many microseconds is the one single bit? And that from that one, inverse value is how many bits per second you are sending. Pretty straightforward. Then numeric value in decimal format. What number that one, that first byte, second, third, fifth, fourth and fifth byte actually are the numeric value. And then corresponding ASCII character set or ASCII characters. So on this, you will take those numbers and find the corresponding ASCII character from that table. So if there is a capital A, you'll find number 65 there. Or if you find decimal 80, that will be P, capital P. There. Good. And I have a hint. There is a not that common word sent on this data. 5 letters. So they are only about 28 to the exponent of 5 different possibilities. I wouldn't go guessing. So just do the engineering way. The second part of the first exercise is the multi-byte. So how about sending a word, ASCII coded numbers in serial line, here time scale 125 microseconds per square. Actually, microseconds should have S with the smaller scales. Okay, need to check that, change that one. But anyways, there is, again, you can see the lowest bit length here, and you can start looking at the bits here. And the trick here is now to separate each of these bytes, sent bytes. So there's a start bit, then 8 bits, then stop bit. And immediately after that stop bit, there's the next data transmission starts. From the next 0 state, that is. The stop bit actually releases the line up back to the idle state. Okay, how many bytes? And what is the contents of the transmission in ASCII? So do some the decoding there from this to the message. Okay, third part has I2C type serial transmission. That is a real clock signal of I2C transmission. So the other one is then must be the data. Okay, and here, how was it? Clock is high while the data goes low. This is start of transmission here. Then there's some delay. It doesn't matter since I2C is basically it has clock signal on one line, data on another one, so it's synchronized again. So you can have pauses on the clock. That's quite typical actually. And then there are these 1, 2, 3, 4, 5, 9 clock cycles, and data is either 0 or 1. So you need to figure out what is the contents of that 9 bits and what is the 9th bit actually. I give you a hint. It's the acknowledgement bit, I think. And then another one here. Another is another byte. So basically there are 2-byte transmission with some acknowledgement bits. So how many bytes? Haha, I gave you the answer. But what is the contents of the transmission in ASCII? Yeah, evidently 2 bytes since there are 2 clock sequences here. But anyways, what is the contents? I'm not giving you that one to you. Okay, the fourth part of part 1, part D, is about long transmission line. This is something that Juho did, was it yesterday or Monday evening? Um, as I said, he has his own home laboratory. And it just happens to have 50 meters of cable, low quality cable. And what happens if you transmit data at 115,200 bits per second? This is a real measurement. And basically you can recognize, okay, that must be the start bit. You can actually read how long it was, start bit, and then you can see the other bits. But thinking of a digital device reading or the transceiver, you might end up reading your data so that the line is ringing so much that you get errors on your transmission. So basically, that is the ringing what you get from that LC part of this transmission line. So practically, well, this doesn't give you any points, but it's quite interesting if you can still interpret the contents of this transmission also. Challenge yourself. So in bad transmission line, the signal may look actually something like that. Lots of ringing. Okay, transmission lines, another part which has another 5 points. And now we go to the simulator environment. So basically, you need to construct the following circuit to test transmission line characteristics. So we have 2 resistors, R1, R2, and we have inductance and capacitance. And actually, that should be the same as, let's see, where do we have the transmission line model? Serial transmission line model. Yep. So we have this transmission line model. This is what the cable manufacturers actually give us the transmission line model. So that's the same model here. So this is model for long transmission lines. You will then use the function generator. Doesn't matter what is the frequency actually, just that it basically 5 volts signal and 2.5 volt the 2.5 volts the offset, meaning it's a square wave from 0 to 5 volts. An oscilloscope at some frequency, it actually looks just like a low pass filtered square wave, which is pretty close to sinusoidal wave. So that's why on this oscilloscope picture I have sinusoid instead of a square wave. Start as a square wave, but remember the low pass filtering double low-pass filtering actually here. So that's how the signal is forming. And then some values. Component values. R1, 10 ohms, R2, 100 ohms. So we have about 10% signal loss on that line, which relates to, say, a few tens of meters of cable. Then we have inductance, SSS microhenry. So your own secret code in microhenries. And this is again inductance, which is roughly good for, say, twisted pair line of tens of meters. Then we have capacitance, the line capacitance, S.SS microfarads. Again, this is quite close to tens of meters of cable. So practically this model here is tens of meters of cable, modeling that. Okay, if you need more accurate or realistic values, a cable manufacturer provides those in their data sheets. And if you do this and start changing the frequency, you actually will see the different waveforms on this end. Okay, in order to successfully receive a signal in Arduino, the signal high value must be above 2 volts and low value less than 0.8 volts. So practically, here you can find the frequency such that either the high doesn't go above 2 volts anymore, or low doesn't dip below 0.8 volts. In this picture, this is still okay, since the low is something like 0.2 volts, much less than low level. And then the high values are actually about 2 and 2 point, almost 3 volts. So basically this is fine for data transmission, although there's the low pass filter that makes this square wave looking smoother. No problem. That's what the transmission line does it. Some of you actually may get some ringing there. Don't worry about it. Just look at the highest values and lowest values. So you should be able to recognize bits 1 and 0 in here. And at some point, everyone would have a situation that it doesn't change anymore enough to make ones and zeros. And you mark that frequency. So your SSN number and what is your highest frequency you got. Still changing the states correctly. Next, change the values to these fixed 700 microhenry for inductor and 6 microfarads for the capacitor. That's basically to simplify the following. If you are using the SSS number, some of you actually will get a little bit harder topic. So now you just, with these values, find again the highest frequency. If you did the connection right and set the values correctly on those the values, one place to make a big mess is to use kilo ohms instead of ohms. So notice that all the resistors here are ohms. Wires are pretty good conductors. That's their principal use. Okay, then part 2b, which is based on the previous measurements. Open this one. It's actually a system which has one the Arduino is sending, another one is receiving and printing the values to LCD screen, and in between we have this nice mess of resistors and inductor and capacitor again. So a tens of meters of line in between of those Arduinos. Let's see what happens if I tinker that. Let's tinker that. Takes for a while. Okay, there we go. If I just click start simulation. Okay, 1 second is sending A, B, C, D, E. For some reason that E, the first time E is here, it always goes as a wrong character here. I have no idea what is going on there. It's some sort of bug. But anyways, data is received just fine. Then you would put your own transmission line here, meaning that 700 and microfarad. Oh, okay. Of course. You have changed this a little bit. Try out various values of L and C and find such values. You get about 10% of byte errors, meaning just about one character on 10 looks funny. So basically, starting point 4 micro henries and 200 picofarads is roughly 4 meters of cheap speaker cable. Okay, when you try different values, basically try to keep the ratio L to C constant. So that's basically for the speaker cable. But anyways, first point, well, now the L and C, when you start observing the data errors, so every 10th character prints out funny, and estimate the simulated cable lengths, so what L and C you used, and then in here use that information to calculate it back to the simulated cable length. And in reality, 4,800 bits per second, you should be able to go to 20 meters, even with the cheapest speaker cable you can find from Clas Ohlson or something like that. But anyhow, remember, this is simulation. Reality is really reality. They should have the same ballpark number. Okay, then part 2b, change the values back to those common 700 microfarads and 6 microhenry. And you will go to the code off that one. Change the serial line speed on here, and same thing on the other one. The speed must match. And see what is the bit rate where you can observe the data error rate of 10% with those LNC values. Okay, 10% error rate. And now the question is, does this result match to part 2A measurement result 2? So how close bit rate you get here compared to the frequency you measured in here. So they practically they should be just about the same, say within some error margin, 30% of error margin. The highest frequency here should match quite closely to the bit rate. So the ballpark number should be the same. Since on that frequency exercise was done so that when do you still match the logic levels, and when you look at this Arduino circuit, okay, this is sending and this is receiving. What are the logic levels for receiving? Well, there are 2 volts and 0.8 volts. Same as for checking the highest frequency for that when the square wave is still going through just fine. Okay. So that's the exercise number 8. And now it's good time to ask questions if you have any. Okay, seems no questions.